Hello and welcome everybody. Today we will be talking about the second half of the first of the fundamental theorem of calculus. So this is going to be the conclusion that will wrap up everything that we've learned with the area under the curve and why is it actually related to all the stuff that we did in the first semester with the derivative. So here is kind of like the big conclusion. So get your party hats on or wherever you want to wear them. Okay, if you don't want to wear anything, that's totally fine. Just don't tell me. Okay, so here first, this we talked about the first fundamental theorem of calculus. Now we're going to talk about the second fundamental theorem of calculus. In some textbook, they actually don't have two parts to the fundamental theorem of calculus. They consider it as one single thing. But I think this is actually something that should be separated because the first part is going to help us derive the second part. So some people just like to wrap everything into one big basket, but not me, unfortunately. Okay, so just to go ahead and recap, FTC1, first fundamental theorem of calculus, it says that if capital F of x is equal to the area under the curve from a to x of lowercase f of t dt, then the derivative of capital F of x is going to be equal to f of x, the lowercase f of x anyways. And the big thing that we have to get out of this is that the idea over here is that if I take the derivative and the area under the curve, they cancel each other out. Okay, so the area under the curve and the derivative cancel each other out, just like positive and negative cancels out, as the analogy that I gave in the past. Or multiplication and division, they cancel each other out. They're kind of like saying inverses of each other. Okay, so here is what FTC number 2 is saying then. FTC 2 says the following. If capital F is the quote-unquote antiderivative of f, meaning that if I take the derivative of capital F of x and it gives me my lowercase f of x, then the area under the curve from a to b of lowercase f of x is equal to the capital F of b minus the capital F of a. So this right here is a big thing because now it's saying that, hey, we can solve for the area under the curve by strictly just finding out what the antiderivative of the equation is, meaning what function, right, is going to, if I take the derivative, is going to be equal to the equation that it's going to be given me. So here are some examples of that, and then we're going to go ahead and talk about the proof of this. So for example, let's say that I want to solve for the area under the curve from 1 to 5 of 2x dx. According to FTC number 2, what I need to do is take the antiderivative of 2x, meaning what function, if I take its derivative, will give me 2x then? Well, that's where the x squared comes in because the derivative of x squared is 2x then. Now, it says that an FTC number 2, we're going to go ahead and take the upper number, the upper bound, and then plug it into the equation, and then minus the lower bound, plug it into the equation. And that's where I got the 5 squared minus 1 squared. So the answer is equal to 24. So the conclusion is that, if I want to find the area under the curve for the equation y is equal to 2x, the area should be equal to 24. And let's just verify just to make sure that is true then. So here's y is equal to 2x, right? Here is going to be 1. And then here somewhere is going to be 5. And I want to find the area of this trapezoid, which is easy enough. The height on the lower part is supposed to be 2. The height on the upper part is supposed to be 10. So according to my area of a trapezoid, then it's going to be 1/2 multiplied by 10 plus 2. And then multiplied by 4 because that is the length of the base from 1 to 5. So multiply everything out. That looks like it's going to be 12 multiplied by 2. So yeah, it does give me 24. So that checks out. Something a little bit more complex where we definitely cannot check though is maybe the following over here. The area under the curve from 0 to 1 of 1 over 1 plus x squared dx. What is the area under the curve of that equation? Well, hopefully you haven't forgotten that the tangent inverse of x, that if I take a derivative, is supposed to be equal to what I have on the left-hand side. So that will be its quote-unquote antiderivative. Now we're going to go ahead and plug in the upper bound minus the lower bound. So tangent inverse of 1, right? And then minus the tangent inverse of 0. Tangent inverse of 1, where is tangent equal to 1? That's pi over 4. And then tangent inverse of 0 is equal to 0. So the answer is going to be pi over 4 then. So what that means is if I go to my graphing calculator, let's say that I have that equation then. So 1 divided by 1 plus x squared, right? And if I go to graph, that's what it's basically going to look like. And now, if I want to find the area under the curve from 0 to 4, well, that's where this guy is, and I'll show you how to do that right there later. From 0 to 1, and then now you can kind of see it. Oh, actually, well, sorry, I guess it doesn't really show. But basically, I'm looking for the area under the curve from this part all the way to this part right here, to 1. So that little sliver over there, that's the area under the curve that I was looking for. And it's supposed to be equal to pi over 4, right? So going back to my picture over here, now let's go ahead and prove why this actually all works out. Why is it that we can just take the antiderivative in order to find the area under the curve? So first, what I'm going to do is I'm going to go ahead and say, let g of x be equal to the integral of a to x of f of t dt. Okay, so this is just kind of like playing on what we did in the last section. And keep in mind that capital F of x, right? Actually, oops, sorry, let me go ahead and erase that. Let me just go ahead and write too, that the derivative of capital F is supposed to be equal to f then, okay? So that is still hold true in this case. Now, according to my first fundamental theorem of calculus, right, FTC number 1, g prime, the derivative, would then be equal to f of x. Okay, just basically getting rid of the integral and plugging in x for t then for the dummy variable. Now, if I go backwards, right, let's go ahead and take the antiderivative of this expression, okay? So take the antiderivative. Okay, so rather than taking the derivative, I want to go ahead and move backwards then. Well, if I go backwards, if I take the antiderivative, f lowercase f becomes capital F of x. And then for g prime of x, its antiderivative will just be itself, the original self, which is going to be g of x. And for record's sake, technically there should be a plus c, because anytime you go backward and take the antiderivative, they all have the same derivative so long as they differ by a constant. If you remember from a while back, we said that if we have y is equal to x squared, and then y is equal to x squared plus 3, and y is equal to x squared minus 5, they all have the same derivative because those constants, they vanish away when you take the derivative. So that's why going backward, we have to put the plus c. All right, so here it is. Here's the moment of magic. Let's go ahead and see what happens here. Let's say I want to try to solve for what is the capital F of b. Well, according to my equation over here, then capital F of b is going to be equal to g of b, right, plus c. Then if I want to solve for what is the capital of f of a, that's going to be equal to g of a plus c. And now, looking at the right-hand side of FTC number 2, I'm going to go ahead and take the difference between the two. So capital f of b minus capital F of a. Well, on the right-hand side, that's going to say g of b minus g of a, and the c's are going to cancel out. And now if we just go back to our very, very original equation over here, we actually know what g of b and g of a are actually. So g of b, that is going to be the integral from a to b of f of t dt, right? And then g of a, well, substituting a into editor for x, that's going to be from the integral from a to a of f of t dt. And if you remember, the area under the curve of a to a, that's going to be 0. So now all we have left is basically our FTC number 2, and that's going to be our proof then. All right. So now we don't have to, dig and grind our way or scratch and claw our way into finding the area under the curve. We could just find the area under the curve if we know the antiderivative of the equation, and we could just plug it in. So here, let's take a few examples, and then afterwards, I think that'll probably do it then, okay? So let's say I want to find, in the first case, the area under the curve of x squared from 0 to 1. So first, what I'm going to do is I'm going to solve for the antiderivative of x squared. the antiderivative is supposed to be x cubed. And according to the power rule, normally we would produce a 3, but because we're working backwards, I'm going to lose a 3. So that means that I should be multiplying by 1/3. So if I take the derivative of this equation, that would definitely give me x squared then. My boundaries are going to be from 0 to 1. So my answer will be 1/3 multiplied by 1 cube minus 1/3 multiplied by 0 cube. And that's going to be my area under the curve, which in this case is equal to 1/3 then. Okay, take a different one just in case. Here, I want to find what is the area under the curve of cosine of t from pi over 3 to pi over 2. So let's go ahead and try that out. What function has a derivative of cosine? Well, that's going to be sine, right? So the derivative of sine is equal to cosine. So that's my antiderivative. Now I'm going to go ahead and plug in the boundaries, the lower bound and also the upper bound, and subtract one from the other. So my area under the curve is going to be the sine of pi over 2 minus the sine of pi over 3. Sine of pi over 2, that's equal to 1. Minus the sine of pi over 3, that is equal to root 3 over 2. So my area under the curve is going to be 2 minus root 3 over 2 then. Okay. All right, just a few more with these, right? Going backwards, I think that's probably, one of the most fundamental things of math. I remember I said a long time ago that for math, the most important thing is, if you know how to go forward, you also need to learn how to go backwards. So that's what all this is about. Okay, so the second part, or the third part right here, let's see. The area under the curve from 1 to e to the 3 of 1 over x dx. What function has a derivative of 1 over x? Well, that, hopefully you guys remember, is going to be ln of x. And then you also are now going to plug in the boundaries from 1 to e to the third. So let's see, ln of e to the third minus ln of 1. So that is going to now be our area under the curve. The 3 can go outside. That gives me 3 times ln of e minus ln of 1. That's equal to 0. So the answer is equal to 3 then. So, just drawing it as a visual so you can see what's happening. Here is the curve of y is equal to 1 over x. If I'm asking for the area under the curve from 1 to some value e to the third, right? This right here, that area is supposed to be equal to 3. Okay? All right. Try a couple more right here, and then we're done. Let's see. I want to find now what is the area under the curve of 2 to the x from 0 to log of 2. Well, again, what function has a derivative of 2 to the x? That should be itself 2 to the x. And then if you remember, for an exponential function, normally it produces an extra factor of ln of 2. Right, ln of the base. So going backwards in this case, I need to divide by that factor. So ln of 2 is divided in this case. And then plug in the boundary of 0 to log of 2 then. So my final answer is ln of 1 divided by ln of 2. And then multiply by 2 raised to the power of log of 2. And then minus ln of 2 in the denominator, multiplied by 2 to the 0. So cleaning each part up. 2 to the log of 2, that is just plain old 2. And then times ln of 2 in the denominator. And then minus the ln of 2 in the bottom, multiplied by 1. So putting it all together, that is just equal to 1 over ln of 2 then. All right? Okay, so hopefully, this area under the curve thing is going to be pretty easy for you. And finally, for this last one, okay, this one is actually going to be a trick question. And I don't know if you guys can see it or not. I'm asking for the area under the curve from -4 to 6 of 1 over x squared. Now, before you jump into taking the antiderivative of this equation, something you should recognize is that in here from my equation, x cannot equal to 0 because it's going to be undefined. So what that means is you actually can't find the area under the curve because all of these functions that we've been finding the area under the curve for, they have to be continuous. So remember all those rules about taking the derivative has to be continuous. The limit has to exist. Going backwards, it's the same idea. It has to be continuous for me to find the area under the curve. So in this case, the quick answer is does not exist. Later on, we'll look at